Hey everyone, and welcome back to part 3 of this video on pipe flow. We previously introduced the idea of head losses in pipes occurring due to friction. In this part, we'll cover another cause of head losses. When we looked at the pipe rig in the first part, we saw from our piezometer readings that relatively large head losses occurred along the straight section of the pipe. For example, here, between the first 3 readings. These losses were due to friction, and we introduced the Darcy-Weibach equation as a manner with which you can quantify these losses. However, there are another source of head losses which are important to consider, and these are known as local losses. Local losses occur whenever a change in geometry takes place in the pipes. By change in geometry, we really can refer to any deviation from a standard straight pipe. However, common examples are things such as bends. Ours was a right angle, but this can really refer to any angle bend. And secondly, expansions or constrictions, where 2 pipes of different diameters meet. At both these changes in geometry, a local head loss will occur. To demonstrate the existence of this local head loss, we placed piezometer readings before and after both one of the bends and the location where the smaller pipe diameter expanded into the larger one. Let's begin by considering the right angle bend. Taking a look at the pressure readings, as always, we can add some blue to make the transparent water easier to see. The pressure readings before and after this bend refer to locations 4 and 5. And when we compare the two, we notice a significant head loss occurring between the 2 readings. Obviously, the friction of the pipe length between the 2 locations plays a role. However, this head loss value is greater than normal for the small distance apart of the 2 readings. This is due to the local loss occurring across the bend, and it has to do with flows separating from the walls, generating additional turbulence in the process. Again, when we compare the readings across the expansion, which in this case refer to locations 6 and 7, we again see a loss. However, it's much smaller this time. This is because the scale of the local loss is dependent on the nature of change in geometry, but also because in the larger pipe diameter, the flow is slower. And so, if you remember Bernoulli's equation, pressure increases in response to a decrease in velocity. Similarly to the Darcy-Weibach equation we use to quantify frictional head losses, we also have an equation with which we can quantify local losses. And here it is. We can express any local loss as being proportional to the velocity head. The new variable here is this value, the proportionality coefficient c. This will vary depending on the specific type of change in geometry. Common examples might be a constriction, where this c value becomes 0.5, a bend, where this c value will vary depending on the angle of the bend. For approximately 90-degree bends, this value again becomes 0.5. And finally, expansions. These are the one case where a change in geometry has a slightly different variation of the formula, which we can see now depends on both the velocity before and after the change occurs. It's important to note these losses are called local because they are localized, meaning they occur in one specific location, as opposed to friction losses which occur across long lengths of pipes. We can see this reflected on our energy gradient line, although the friction losses are displayed as gradual linear decreases. The local losses are represented by a sudden drop in energy. And we can now see that our total head loss across this section is simply a sum of all the frictional and local losses. Local losses are sometimes referred to as minor losses, and this is because the head losses they incur are relatively small compared to those caused by friction in typical applications. Over large-scale pipelines which run multiple kilometers, they are sometimes neglected. However, upon smaller scale pipe combinations, such as the pipe rig here, we can see that they do account for a significant portion of the head loss, and therefore should not be forgotten. Now that we have equations with which we can quantify both the friction and local head losses, in the next video we will try and use this knowledge in our first worked example.